Okay, so welcome to the next lecture. We were talking about ordinary differential equation with variable coefficients, and then in the last lecture we actually looked at a specific case when the coefficients are constant, okay, P and Q. So I think I have given you a method for solving this second order differential equation. Is that first you look at the homogeneous equation, find the general solution of that, involving two constants C1 and C2, right? First you need to find two linearly independent solutions, right? Then take the linear combination, that will give you the general solution of the homogeneous equation, and then you find one particular integral which satisfies the entire non-homogeneous equation, add them, and that will be the solution of the total equation. So now today I am going to look at couple of different methods for finding the particular solution of the non-homogeneous equation, okay? So you will see that the idea is really, how do we do it? It's a really interesting thing, but one method is method of variation of parameters, which I am going to talk about. Second method is basically involving operator theory. So how operator theory, and there are actually three sub methods in operator theory, like series expansion, and then by partial fraction and other kind of things, right? So we'll talk about that. So basically today first we look at method of variation of parameters for finding particular solution of a non-homogeneous second order differential equation, number one. Number two, then we are going to look at operator theory, right? So basically those three methods in the operator theory, how do we do that? And then we also briefly give you an idea when the equation order is more than 2. So if it is nth order equation, so idea is exactly simple, what the way we have told you. So either if the roots are complex conjugate, then what has to be done, distinct real, then what has to be done, and so on and so forth, right? Or if there is a repeated root, right? So without any proof, I will mention those results, okay, for higher order equations as well, right? I think after finishing all this, I think if we have time today, or otherwise probably in the next class, there is another very interesting theory for solving differential equations, which is known as power series. And power series method is very powerful method. So what you do, you assume that the solution is of the form of a series, summation ai, right, x raised to power n, right? So basically, or summation a n x raised to power n is equal to 0 to infinity, right? That kind of series you can substitute. Or it could be summation n is equal to 0 to infinity a n x minus a whole raised to power n. Those kind of power series is a solution. Substitute it, solve for the coefficients ai's, and you are done. And there are different techniques there developed by Frobenius himself. But I think this time we are not going to do too much series, but I will give you idea how it works by giving you two specific examples. For example, if y double dash plus y is equal to 0, how we will solve this using power series method. I will give you the examples, right, how that works. Normally we used to cover these power series methods in details depending upon the type of differential equation it is. It may have some singular points or other things, right? So then there are different methods. How do we do that? So basically in some cases we assume the solutions of the form y is equal to x raised to power m times power series, and then you seek the solution. Those kind of methods. See, remember that x coefficient we multiply if there are issues, right? So those kind of techniques are there. And I think after that we are going to look at partial differential equation, probably one lecture on that, and then Laplace transform, and I think probably that will be sufficient. If time permits, we can look at beta and gamma function and some spatial functions. By the way, solution of some of the differential equations are known as spatial functions, and like Bessel function, different kind of functions, and there are different kind of equations like Bessel equations of certain order. So these are all second order or certain order differential equations, and the solution turns out to be in the form of a series, okay, and that satisfies certain properties. So this is really very, very important actually, and that's how actually Fourier came into the idea of Fourier series. Okay, that's something really very, very important, which was later developed into Fourier transform. So okay, this is something very fundamental. So I think you may look at the notes of the series solution, if you want to know more about it. But so let me start this finding a particular solution of a non-homogeneous differential equation. By the way, for the projects, I would like to again tell you that please maintain a log book. It's very, very important that everybody is writing every day what they are doing in the project. Each member of the team, right? So they may be playing, not did anything. So you can write that I have not done anything today. Okay. So that way we can check what you are doing. Anyway, so this is our, equation 1. So y double dash plus px times y prime plus qx times y is equal to rx is our linear second order non-homogeneous differential equation with variable coefficients, right? And we want to find now, so you know that if you want to solve this, you look at the homogeneous equation, solve for the general solution of the homogeneous equation, and then you find out somehow the particular solution, right? What is written there? I think this should be general solution, right? I think I don't know why it is not properly coming. General solution, right? GS, okay? Then you add the particular solution. So now I will tell you the method for finding particular solution. Okay, so assume that equation is this is our non-homogeneous equation. I want to find one particular solution of this equation. And if you look at the homogeneous equation, which will be right, we look at the homogeneous equation. And suppose I find two solutions, y1 and y2, which are linearly independent. So we have the general solution as c1 times y1x plus c2 times y2x. This is our general solution of equation 2. Right. Okay. This is known. Okay. So somehow you found the homogeneous equation general solution, right? Now I need to find one particular solution of the non-homogeneous equation. So what I am going to do, see, these are all very, so we have these constants c1 and c2, right? So I am assuming that these are not constant anymore. These are though parameters. I will vary them. So that's why this is known as method of variation of parameters. I will say that c1 is some function of x, c2 is some function of x. I don't know what. I need to find those values, and then you substitute it here and solve for v1 and v2. Right. So I assume that. So this is method of variation of parameters. We seek solution of the form y is equal to v1 of x times y1 of x plus v2 of x times y2 of x, and we substitute this in equation 1. But what are v1, v2? We don't know. I need to find those values. Okay? Gotcha? So basically I am varying the parameters. c1, c2 were parameters, constant, right? I am saying that now in place of constant, we have two functions, v1x and v2x. I don't know what are their values. Now I will substitute this expression into equation 1 and solve for v1 and v2. So we substitute here, we are going to get the following. So basically y prime will be v1, y1, v1, y1 prime plus v2 y2 prime plus v1 prime y1 plus v2 prime y2. I am not writing function of x, just prime means derivative, right, with respect to x. Now so I'll put it in brackets. Okay. Now can anyone tell me what should I do? आपको लगता है कि if I put this expression into this and I compute y double prime also, and I will be able to Is there a method? How do we solve for V1 and V2? Any idea in the class? How do we solve for V1 and V2? V1 V2 is not known. I don't know what is the value of V1 V2, right? So essentially, since V1 V2 are two unknowns, I should have at least two equations, right? But here there is only one equation. So what should we do? यहाँ पे थोड़ा सा clever trick की जरूरत है, right? Right. So I found y prime. Similarly, I can find y double prime. I will substitute, right? And there is a more messy equation that we are going to get, right? So now, clever person, what they will do? Since I am not looking for general solution of the non-homogeneous equation. I need to find one particular solution, right? So somehow I need to find, right? So what I can do? I'll say, okay, suppose I am looking for only those V1 and V2 for which this is 0. This will simplify my task, right? Because now you see, if this is 0, I have two equations, right? I can solve for V1 and V2. And anyway, I need only particular solution, so it's okay. I'm not worrying about the general solution, right? Got it? So I'll say that suppose this is 0. I am only looking for those V1 and V2 for which this expression is 0, right? So this will give us V1 prime y1 plus V2 prime y2 is equal to 0. This is 1. And then actually then y prime will become V1 y1 prime plus V2 y2 prime, right? Because this portion is 0. So you are left with this portion only, right? Y prime is this. So I can also again compute y double prime then. V1 y1 double prime plus V1 prime y1 prime plus V2 y2 double prime plus V2 prime y2 prime. Now I can substitute these values of y prime and y double prime in the expression. It turns out that we are getting V1 times y1 double prime plus py1 prime plus qy1 plus V2 times y2 double prime plus py2 prime plus qy2 and plus v times, so v1 prime y1 prime plus v2 prime y2 prime is equal to rx. After substitution after substituting the value of y prime and the value of y double prime into the equation 1, which is the non-homogeneous equation, rearranging, taking the v1 and v2 common, and the rest of the things is equal to this, right? Now what happens to this? Since y1 is a solution of the homogeneous equation, this will be 0, right? And y2 is also a solution of a homogeneous equation, so this will be 0 also. So these two terms will be 0. So this is 0 and this is 0. So we are left with v1 prime y1 prime plus v2 prime y2 prime is equal to rx. Okay. So actually we have got two equations, this one and this one. Now we have two equations, two unknowns. I can solve for v1 and v2, right? Okay. So I can now solve it. I am just now writing. So here actually we are going to use some method which you know from your high school. v1 prime is equal to minus y2 times rx divided by w of y1 y2, Wronskian of y1 y2, and v2 prime is equal to y1 times rx divided by Wronskian of y1 y2. This is a valid solution because Wronskian is 0, because y1 and y2 are linearly independent. That is our assumption anyway, right? So this implies that v1 is integration of minus y2 rx divided by w y1 y2, and this implies that v2 is equal to integration y1 rx divided by Wronskian y1 y2 dx. Okay. So now we have since we have v1 v2, solution will be what? y1 times v1 plus y2 times v2, right? This is our particular solution of the equation, right? हमको चूंकि एक ही सोल्यूशन चाहिए, कोई एक सोल्यूशन किसी तरह से मिल जाए, दैट्स व्हाट आई वांट, दैट्स ऑल, बाकी हमें कोई मतलब नहीं है, राइट? सो वी आर एबल टू डू दैट ना. सो नाउ given a non-homogeneous equation, I can compute these values, right? As long as y1 and y2 is known, right? I think I have written, yeah. As long as y1 and y2 is known, I can find out v1 and v2, and then So let us take a quick example. Equation is y double dash plus y is equal to cosec x. So homogeneous equation is y double dash plus y is equal to 0. So general solution is c1 times sin x plus c2 times cos x. General solution of the homogeneous equation, right? So Wronskian of y1 y2 is -1, which is not equal to 0. This is y1, this is y2, right? I can compute those things. So v1 is nothing but integration minus cos x divided by -1 dx turns out to be log of sin x, and similarly v2 is integration sin x cosec x divided by -1 dx is equal to minus x. So the solution, particular solution is y is equal to sin x log of sin x minus x cos x. Right. Okay. So this is the way for finding one particular solution, right? As long as you know the general solution, you can find a particular solution, right? Technique is very simple. Okay, so now I think I am going to tell you something for higher order differential equations, and then we will come to the operator method after that. So higher order differential equation, I am looking at only with constant coefficients. A n y. Fx is a function which is continuous on closed interval a comma b, right? So this is our general equation. Coefficients are constant, right? Nth order differential equation. So this is known as non-homogeneous linear ordinary differential equation with constant coefficients, right? This is how you read it. नाम बहुत बड़ा है इसका, but it's okay. So the general solution of this equation will be y is equal to y general solution, right, plus particular solution, right? What is the general solution? Look at the homogeneous equation and solve, right? So homogeneous equation will be y nth prime plus a1 y n minus 1th derivative plus a n minus 1 y prime plus a n y is equal to 0, right? So there, remember what we seek a solution of the exponent form and so on, right? So you get a auxiliary equation. So in this case, if you put y is equal to e raised to power rx, here equation is rn plus a1 times r raised to power n minus 1 plus a n minus 1 r plus a n is equal to 0. This is our auxiliary equation. अब इसके रूट पे डिपेंड करेगा what are the solutions. Remember, linear independent solutions we need to find. So basically, if the roots are distinct, suppose there are n distinct roots of this equation. So case when r1, r2, rn are distinct roots, in that case solution is c1 times e raised to power r1x plus c2 times e raised to power r2x plus dot 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 cn times e raised to power rnx, right? Just like there m1, m2 are distinct roots, so y is equal to c1 times e raised to power m1x plus c2 times e raised to power m2x, right? So if roots are real and suppose they are equal, so r1 is equal to r2 is equal to say rk, certain number of times, yes, it's a real root. In that case, what will happen? Solution is something like c1 plus c2x plus c3x square ck x raised to power k minus 1 e raised to power r1x. Sorry, r1x. Solution is this, right? Okay. Remember, there was term, first solution was e raised to power mx when the roots were real, real and equal. And the second was x times e raised to power mx, if you remember, recall from your previous days, right? And then you combine them, it was c1 plus c2x times e raised to power mx. Here, this is expanded, that's all, okay? So, k is basically multiplicity, how many times it is repeated, okay? So, if roots are complex, so you know that complex root always occur in pair. If a plus ib is a root, a minus ib is also a root, right? So, in that case, so suppose a plus ib and a minus ib is a root, okay? And suppose they are repeated certain number of times. So, suppose the multiplicity is again k, so the solution is e raised to power ax, a1 plus a2x, ak x raised to power k minus 1 cos bx plus b1 plus b2 x plus bk x raised to power k minus 1 sin bx. This is a part of the general solution, okay? So, without going into further details or proving anything, I just wanted to mention this, that if roots are real and distinct for higher order, take the linear combination, because in that case you can show that e raised to power r1x, e raised to power r2x up to e raised to power rnx are linearly independent. Their Wronskian is non-zero. So, you may ask, by nth order के Wronskian की definition क्या होगी, right? हमने तो 2 second की बताई, 2 by 2 की, y1 y2 y1 prime y2 prime, that was a right determinant of that. Here it will be y1 y2 y2 yn, then you differentiate once, differentiate twice up to nth differentiation, right? So the whole thing is generalized as it is, okay? So Wronskian can be generalized, okay? So not going too much, but at least one example I can do. Suppose fourth times derivative minus 5 double prime plus 4y is equal to 0. Auxiliary equation is r raised to power 4 minus 5 times r square plus 4 is equal to 0. Now you see that this is nothing but r minus 1, r plus 1. Factor कैसे करेंगे? I guess that is a high school problem. So general solution is c1 times e raised to power x plus c2 times e raised to power minus x plus c3 times e raised to power 2x plus c4 times e raised to power minus 2x. Right. So depending upon the auxiliary equation case, you can actually find out the values. Okay, so this was about the higher order. Now I am going to look at operator method. That's pretty beautiful method. Operator method. So there are 3 methods which I am going to tell you. Okay. So it is given that dn of dxn of y plus a1 times dn minus 1 y of dxn minus 1 plus an minus 1 dy by dx plus any is equal to fx, right? This is our equation. So now nth order differential equation with constant coefficients. So I will put d of y as dy by dx, d square of y is equal to d2y over dx2, and so on. D nth y is equal to dny over dxn. It's like an operator. Okay. So this whole thing will simplify to d raised to power n plus a1 times d raised to power n minus 1 plus dot 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 a n minus 1 times d plus a n times y is equal to f of x. Right. Operator. So d square means differentiating twice. D cube means differentiating 3 times and so on. Right. So this whole thing I can call it as P of d. So P of d times y is equal to f of x. So solution y is nothing but 1 over P of d times f of x. So this is what. Now what do you mean by 1 over P of d? I am going to show you depending upon the structure of this polynomial, P of d. So suppose P of d is d minus 1 into d minus 2, or suppose P of d is d minus 1. So essentially what is the meaning of 1 over d minus 1 of f of x? I can simplify and find a formula, and then I will use it quite often. Okay. So let us see how this operator system works. Okay. So let us take a simple case first. Right. D of y is equal to f of x. First order. Okay. So in that case, y is what? 1 over d times f of x, which is simply integration of f of x dx. Right. First order case. So 1 over d square means integrating twice. Right. Integrating twice. Now consider this kind of quantity, d minus r times y is equal to f of x. Because what happens when we look at P of d, this is a polynomial, right? And if it has n roots, the roots will be say d minus r1 times d minus r2 and so on. So a typical root will be d minus r. Okay. So something like that. So I am going to look at that quantity. What happens to this d minus r times y of f of x? So this implies that y is equal to 1 over d minus r times f of x. Right. Now this equation is nothing but, I can simplify, this will be dy by dx minus r times y is equal to f of x. Right. If I just open the operator, right. So this is a first order differential equation, you remember? First order differential equation, I know how to solve it. So solution turns out to be y is equal to e raised to power rx integration e raised to power minus rx f of x dx. Right. This implies that we have got a formula that 1 over d minus r times f of x is equal to e raised to power rx integration e raised to power minus rx f of x dx. Nice formula. Okay. Because the first order equation I know how to solve, I just use. So that means whenever 1 over d minus r times f of x is there, we are going to write something like this. And this formula is now very useful. Now, first method, suppose P of d operator, we can factor it as d minus r1 into d minus r2 and so on, d minus rn, right. So in that case, basically y will be what? 1 over P of d times f of x is equal to d minus r1, 1 over d minus r2 and so on, 1 over d minus rn of f of x. So actually what I am going to do now, take f of x, apply d minus rn by that formula which I have written. You got some value, that is a new fx, then operate this, and one by one you can keep on doing this, right, until you exhaust everything. Okay, so that way you can calculate. So let us take an example. This is method 1. So if you have d square minus 3d plus 2 times y is equal to x times e raised to power x. Actually, sorry, equation is y double prime plus, y double prime minus 3y prime plus 2y is equal to x times e raised to power x. This is our equation. So operator will become this plus 2 times y is equal to x times e raised power x. Factor it, this is d minus 1 into d minus 2 times y is equal to x times e raised power x. So y is 1 over d minus 1, 1 over d minus 2 times x times e raised power x. First apply this operation and then apply the second operation. So this is nothing but 1 over d minus 1. This whole thing is nothing but e raised power 2x integration e raised power minus 2x x times e raised power x dx, right? Yes, 1 over d minus 1. This whole value is minus 1 plus x times e raised power x. You can simplify, right? So basically this I can simplify and we arrive at something like this. Now I can apply 1 over d minus 1 on this. Now our new function f of x is this, right? So I can just apply that. So then y is equal to actually 1 over d minus 1 minus 1 plus x times e raised power x. Y is equal to 1 over d minus 1 minus 1 plus x times e raised power x, right? So this is nothing but e raised power minus integration e raised power minus x 1 plus x e raised power x dx, and then simplification gives you minus half times 1 plus x whole square times e raised power x, right? All this integration steps I am just leaving for you, right? So essentially you factorize f of d is equal to d minus r1, d minus r2, d minus rn, or one by one you can keep on applying, right, until you exhaust everything. This is method 1, right? Now I am going to look at the second method. So this is a particular solution, right? So as an exercise, I mean, you can do this. Y double prime minus y is equal to e raised power minus x. Find particular solution, right? Operator banao, factor karo, and you can apply the formula, right? So method 2. So let me show you method 2. Y double prime minus 3y prime plus 2y is equal to x times e raised power x. So I think वैदिक मैथमेटिक्स में आपने पढ़ा होगा पार्शियल फ्रैक्शन कैसे करते हैं, राइट? सो ऑपरेटर विल बी, सो सॉल्यूशन विल बी व्हाट? y is equal to 1 over d minus 1 into d minus 2 x times e raised power x, right? Now this is nothing but 1 over d minus 2 minus 1 over d minus 1 times x times e raised power x. ये कैसे आया? पार्शियल फ्रैक्शन से, राइट? दिस होल थिंग कैन बी पार्शियल फ्रैक्शन. अभी क्या है, अलग अलग लगा दो, यहां फॉर्मूला लगा दिया, वहां फॉर्मूला लगा दिया, एंड वी आर डन. सो इन द प्रीवियस मेथड एक वन बाय वन वी आर ऑपरेटिंग, राइट? 1 over d minus r1 minus d r2 and so on. Here do the partial fraction and then calculate it. So this is 1 over d minus 2 x times e raised power x minus 1 over d minus 1 x times e raised power x. This is, so I am not computing, I will leave it for you to verify that this is nothing but this minus 1 over half x square times e raised power x turns out to be minus 1 plus x plus half times x square times e raised power x. ओके, यहाँ के स्टेप मैंने उड़ा दिए हैं, राइट? वो फॉर्मूला सीधा लगाया है, राइट? Okay, so we arrive at particular solution. This is method number 2. So now third method is series expansion. Okay, again take an example. So y triple prime minus 2, sorry, y triple prime minus 2 y double prime plus y is equal to x raised to power 4 plus 2x, x raised to power 4 plus 2x plus 5. Okay, so operator equation will be d cube minus 2d square plus 1 times y is equal to x raised to power 4 plus 2x plus 5. So sometime when the operator is something like that, we are not able to easily do the calculations, right, the partial fraction things and so on. Now we can use series method. That's pretty neat thing to do. So then y is equal to what? 1 over 1 minus 2d square plus d cube of x raised to power 4 plus 2x plus 5, right? I can write this is our whole thing. Now I can open, so if we can treat it like 1 over 1 minus x is what? Series expansion. 1 plus x square plus x cube dot 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 dot, right? 1 over 1 minus x, right? So I am just going to treat this thing as a series. So y is equal to nothing but 1 plus 2d square minus d cube plus 4d raised to power 4 minus 4d raised to power 5, and this power I need to go depending upon what is the highest power there. उसके बाद की जरूरत नहीं है, right? Dot 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 x raised to power 4 plus 2x plus 5, right? So now d square means differentiating twice, d cube is differentiating 3 times. Keeping those things in mind, y turns out to be x raised to power 4 plus 24x square minus 22x plus 101. You can actually solve for it, right? So series expansion. So 1 over 1 minus x kind of thing I am using here, right? Minus you can take out, and this is nothing but 2d square minus d cube. Expand it, right? Okay, and then apply. The highest power we need to take, because we are taking only up to 5, because the highest is 4 here, right? Okay, so that everything is taken care of. One nice property which I have, I should tell you, if it's known as shift rule. If f of x is of the form e raised to power kx g of x, then we have some shortcut. So in that case, d minus r times f of x is nothing but e raised to power kx times p of d plus k times g of x. In other words, we apply this formula that 1 over p of d e raised to power kx gx is nothing but e raised to power kx. You can take out 1 over p of d plus k times g of x. This is a nice formula. Why it works? Let us see here. Okay, whenever the function f of x is some exponential times another function, we take e raised to power kx before the operator, and so the operator which was operating with respect to d will become p of d plus k. So it's known as shift rule. So why it happens? Let us see. So if you look at what is d minus r times f of x, is nothing but d minus r times e raised to power kx times gx, because this is how fx is, right? Now this is a single operator. This is a single differential operator operating on the product of two functions. So differentiation of first times second plus differentiation of second times first. Product rule of the differentiation, I am going to use it, right? So the whole thing becomes d minus r. Okay, yeah. So this is nothing but, e raised to power kx first function times differentiation of second. So d minus r times g of x. I'm just opening the bracket. So this is d of g of x plus k times e raised to power kx gx minus r times e raised to power kx gx. Do you agree? So I am saying that this whole expression you multiply with the d minus r times e raised to power kx gx, which is here, right? And then I am operating d on this product. So that is this, right? So now I can simplify this. So if we simplify this, actually we are getting d minus r times f of x is equal to e raised power kx d plus k minus r times g of x. So in other words, PD of e raised power kx times gx is equal to e raised power kx times p of d plus k. So there is shift like this in general, right? So that's why we have this result that 1 over p of d e raised power kx gx is nothing but e raised power kx 1 over p of d plus k times gx. This is the formula that we can use, known as shift rule in the operator, right? So whenever function has exponential form times this another function, take e outside of the operator and then you are just shift it here d plus k. Okay, so let us take an example and I think it will be clear to you. Y double prime minus 3y prime plus 2y is equal to x times e raised power x. So operator is d square minus 3d plus 2 of y is equal to x times e raised power x. So y is nothing but 1 over d square minus 3d plus 2 times x times e raised power x. E raised power x times x, e raised power x I can take on the other side. This is 1 over d plus 1 whole square minus 3 times d plus 1 plus 2 times x. Okay, so overall expression simplifies to this e raised power x times 1 over d minus 1 x, right, d square minus d, and then you know one by one you can operate, right, on x, and actually you are going to get minus e raised power x. You can just check that you are getting this half of x square plus x plus 1. I think this is the same question that we have done earlier here also. You see this one actually, right? So same question becomes a bit easy also sometime when you use this shift rule. Okay, so I think that's all for finding particular solution. Next class, which is tomorrow, right, 8 o'clock in the morning, we are going to look at series solution. I am going to give you two examples, and then after that we are going to look at what is there? Partial differential equations. Okay, so then we'll talk about partial differential equation. For partial differential equations, although for engineers there is book, which I told you, right? Whatever material till now we have covered is there in the Simpson's book, right? Differential equation with applications. I hope you are reading. If you are not reading, you are on the wrong track, right? That's what I can say, right? Now, second thing is that differential equation बहुत आसान topic है. Whenever I gave exam the first time, it was full marks, right? So you can also get full marks. It's very easy topic, right? So now what happens after this? For partial differential equation, there is another very interesting book, Sneeden, I.N. Sneeden, Elements of Partial Differential Equation. If you are really you're overexcited to want to read more, right? But otherwise, that differential equations for scientists and engineers, that book has some material, and also that Jan book or Crazy book also have them, different things on this. Okay, thank you very much.